5.3, we're going to explore growth, and we're going to look at different kinds of growth. So to help motivate that, let's look at this first example here. You're hired at a new job and are offered the following two options for your retirement plan. Option 1, when you retire, your employer will pay you $2,500 for each year you are employed. Option 2, when you start your job, your employer will deposit $2,000 in your retirement account, and then your account will earn 12% annual interest for each year you are employed. That is, your balance will increase by 12% each year you are employed. And so the question is, which option would you select? What considerations should you take into account when making your decision? And we're going to explore this question and others like it in this section. So we're going to come back to this question. You may want to pause the video and think about it for a second, but we are going to come back to it after we look at a couple other problems. So let's look at activity 1. Constant growth versus constant percent growth. Now, if we look at these two options up here, we have these two different kinds of growth, constant growth versus constant percent growth. So option 1 is constant growth of $2,500, whereas option 2 is a constant percentage growth of 12% each year. So we're going to explore that a little bit down here with a timely example. A pandemic is sweeping the globe and case numbers are on the rise. On April 1st, 2020, the city of Coronapolis reported 250 positive test results. Question number 1. Health officials first suspect that Coronapolis will see, on average, 75 new cases reported each day since April 1st. Complete the table and then graph this data on Desmos. What kind of relationship is this? Explain. So I really want you to pause the video, complete the table, go to Desmos, see if you can do this scatter plot here, and then restart the video and we'll take a look at it. So I'm going to guess that most all of you had no trouble at all getting these first 4 days here. All right, just adding 75 to each of the previous days. But now we see a jump, and we're jumping to 15 days. Now we could kind of keep track and expand our table and add 75, add 75, add 75. But what we want to do is try to look for a pattern where we could compute this a little bit easier. So let's think about how we got to, say, day 1, right? So let's see, let's write this in a different color. So day 1, we got this number 325 by taking 250 cases plus 75, right? And day 2, we had 250 cases plus, we added 2 75s, right? We added 2 75s because it was 2 days since the beginning, since April 1st. All right, and then to get to 3 days, we really did 250 plus 75 plus 75 plus 75. That's 3 75s that we added on, right? Adding 75 3 times is the same as multiplying 3 times 75. Repeated addition, right? That's how you get multiplication. So hopefully you can kind of see the pattern here, right? So the 4th day, we really added on 4 75s. So a quick way to get to the 15th day is to think, well, if I'm starting from April 1st, I'm going to have to add on 75 15 times. And to get to the 30th day, I'm going to have to add on 75 30 times. All right, so if we do those computations, we should get 1,375 for day 15 and 2,500. Let's come back to this T here in a minute, and let's go look at this graph. All right, so here's the table in Desmos, and we see our points. You really need to make sure that you've got your X and Y axis where you want them. Remember, you can hit Shift, and watch my cursor shift. It changes, and then I can pull this down and up to get a nice easy, where I want this to be. Okay, and I'm looking, whoa, I didn't want to do that. Okay, now we can fix it. there. We'll pull this over to 30. We'll pull this. Now I'm looking here. I got to go up to 2,500, so I need to make sure I pull that down so I'm to 2,500 on my y. So those points certainly look like they are in a straight line, don't they? So let's go back over here and take a look at B. Graph this data on Desmos. What kind of relationship is this? You remember what it's called when your data comes out in a straight line like that? A line, it's a linear relationship. And our main characteristic of a linear relationship is a constant rate of change, right? And so that rate of change is here, 75 cases per day. And that's the answer to C. What is the rate of change? So 75 cases per day. Part D asks us to write an equation relating the number of confirmed cases C to the number of days T since April 1st. So that's really what we're doing down here in this last piece of the table. Okay, so let's notice our pattern here. When we had one day, we were multiplying the 75 by 1. Basically, we didn't really have to write that down, but we could have. And adding it onto the 250. When we had 2 days, we were taking 2 times 75 plus the 250. When we had 3 days, right, when we have 4 days, 15 days, 30 days, all right, so T days, if there were T days, then we'd have 250 cases plus T days times 75. All right, so that's going to be the number of cases that I'm going to write over here. I can't figure out exactly what it is. I can only write an expression for it because I don't know the exact number of days. It's just T days. All right, so the number of cases is going to be 250 cases. That's what we started with on April 1st, plus however many days times 75. Now we could write this a little nicer like that, 75T. But if you put T times 75 in parentheses, that's great as well. Okay, hopefully this is really important right here, so hopefully you're understanding this. How many cases did you start with, and how many are you adding each day in this case? So we're going to go to Desmos and graph this, all right? We're going to go over to Desmos, and right below our table here, we're going to click right there, and it's going to create a new space for us. And we're going to put in the equation we just did. C equals 250 plus 75T. All right, so what do you notice? We have this line, and this line represents all the possible points for all the cases in all the days, not just the ones we did in our table. So I could come over here to 10 days and click on this, and the ordered pair pops up. It says after 10 days you'll have 1,000 cases. Right after, it's hard to get it sometimes right on the nose. After 20 days you'll have 1,750 cases, and we can get all the data that we need by looking at all the points on that line. Pretty cool, huh? All right. Let's take a look at the next example. Now suppose that health officials are equipped with better testing mechanisms and are able to test people in Coronaopolis more efficiently. This, together with an updated report from the Centers for Disease Control and Prevention on how the virus spreads, indicates that the number of reported cases will rise by 15% each day since April 1st. Now complete the table. All right, so we still have our 250 cases on April 1st, but instead of increasing by a constant 75 cases per day, we're going to increase by 15% per day. So before we complete the table, do you remember the multiplier for an increase of 15%? That's going to be the easiest way to do this. Remember when we studied percent increase? So if we're going to do an increase of 15%, we're going to multiply by, do you remember? We'll have our 100% that we started with, and we're going to increase by 15%. So that's 115% of the original value, which means we're going to multiply by 1.15. All right, so the next day, we're going to take the 250 and we're going to multiply by 1.15. And that's going to represent an increase of 15% above and beyond the 250 cases we started with. All right, so I want you to pause the video again, then you're going to go back over to Desmos and you're going to graph this data on Desmos and take a look and see what it looks like. So do that and then restart the video when you're ready. Let's take a look at the first entries you have in your table. Now I rounded these to the nearest person or nearest case, so if you're off by 1 from me, that's fine. Maybe you didn't round as you multiplied, but that's fine. So we're repeatedly multiplying by 1.15. So now we're at this point again where we need to jump to 15. And we could keep multiplying by 1.15, but we want to work a little smarter here. So let's think about, say, how we got to this 2, how we got this 331. We started with our 250 cases, and then we multiplied by 1.15 twice. I think you guys are pretty good at this idea. So we multiplied by 1.5, then we multiplied by 1.15. Right? So that's really the same as taking 250 and multiplying by 1.15 to the second power. How did we get this 381 right here? How did we get this 381? Well, we took 250 times 1.15 times 1.15 times 1.15. So we really took 250 times 1.15 to the third power. And to get the 4, we're going to take 250 times 1.15 to the fourth power. So the quickest way to get to 15 is to think, well, I'm going to start with my 250 cases. And then to get all the way down this table, I'd have to multiply by 1.15 15 times. And to get to 30, I'd have to take 250 and multiply by 1.15 30 times. All right, so if we do that on your calculator, you should get 2,034 cases on the 15th day and 16,553 cases on the 30th day. So before we look at the T part of this, before we generalize here to a formula, let's go ahead and go to Desmos and take a look at this graph. All right, so here's our table, and you really have to, go up high here on your y-axis to access this point here. And it almost looks like it's not really part of the data, but it is. And if you ignore the 30 and we just look at these, oops, there we go. And we just look at these. So let's look at these. Almost look like they're in a straight line, but they're really not quite in a straight line. There's this kind of curve thing happening. This curve, and we're going to see that when we get the equation. All right, so I'll pull this back down so we can get all the way up to 16,000, and then pull over this way and we can see that other point. There we go, right there. All right, so this is definitely not linear, is it? I mean, it's really growing and taking off here once we hit probably about 15, and it's going to take off like that. All right, so is this a linear relationship? No. No, these points are not in a line, right? And you can explain that. All right, let's go take a look at this equation and see if we can write this out. Now, what you're looking for is this pattern as how does the days since April 1st come into play when you're calculating the cases confirmed. So hopefully you can see those days are the exponent, because that's how many times you're going to have to multiply by 1.15. And it's also true for the 1, right? We did 250 times 1.15, which is really 1.15 to the first. And we've talked about this a while ago, but it also works for 0, because anything to the 0 power is 1. So this is, if you punch into your calculator 250 times 1.15 to the 0, you're going to get 250, because 1.15 to the 0 is just 1. So it's 250 times 1. So the pattern works all the way down the table, which is exactly what we want. Okay, so for this t value right here, this t has to be the exponent. So we will take 250, and then we're going to multiply by 1.15 t times. However many times is the same as the number of days, right? However many days past April 1st, even if it goes into May. So the number of cases, I'll write over here, 250 times 1.15 t. Question number C says, is the rate of change constant in this scenario? And the answer is no, because it's not linear. But you could also actually calculate the rate of change. Let's do that for a couple of these. Let's see. When we're looking at rate of change, we're going to see how many cases are being added. So from day 0 to day 1, if we subtract 288 minus 250, we'll see that we added 33 cases. From day 1 to day 2, if we subtract 331, take away 288, that's going to be 43. So already we can see I don't have a constant rate of change. If I subtract these two, I'm going to get 50. All right, oops, I made a little mistake here. Right here, this first one, 288 minus 250, that's 38. I don't know why I said 33. Okay, so 38. So we could see anyway that it's not a constant rate of change. Actually, what's happening is the change is getting greater and greater and greater each time if we kept going through this, because we are taking 15% of a larger number each time. As the cases get bigger, you're taking 115% of a larger number. The increase is 15% of the original amount, or whatever that day was. These numbers right here are 15% of the day before. And if the day before's number is bigger, keeps getting bigger, then these increases are going to keep getting bigger as well. So we do not have a constant rate of change. It's actually increasing. All right, so we actually did D already. Write an equation relating the number of confirmed cases C to the number of days T since April 1st. So we said the cases are going to be the 250 we started with on April 1st, and then we're going to multiply that by 115%, or 1.15, to the power of however many days after April 1st we're looking for. Let's go to Desmos and punch this equation into Desmos, just like we did with the linear one. All right, so we're going to come over here and we're going to go C equals 250 times, and the times is right above the 8, the shift with the little asterisk thing, 1.15 to the power, and above your 6 is a little up arrow. That's your exponent. So you go shift 6 to get your exponent, and T. And there we go. So that's what that graph looks like. So we can see this kind of a shape. This is the shape you're going to get when you have percent growth. And this is actually called exponential growth because of the exponent. I did a capital T. Doesn't really matter. My caps lock. Same graph. Okay. All right. That's what exponential growth is going to look like. If this trend were to continue, how many cases would Coronaopolis report on May 31st? Do you think it's reasonable to assume that this trend will continue through May 31st? All right, let's think, how many days would that be? Do you guys know how many days are in April? April has 30 days. So if we go all the way to May 31st, how many days is that from April 1st? Right, April 1st through May 31st. Well, we got 30 days in April plus 31 days in May, so that's going to be 61 days. So the number of cases will be 250 times 115%, or 1.15 to the 61st power. That will give you the number of cases 61 days after May 1st, or sorry, after April 1st, which will be May 31st. All right, punch that in. Let's see what kind of crazy number we get here. All right, my calculator is saying 1,095,999.686. No, I take that back. I think I must have typed something wrong here. Let me repunch that in. Okay, let's try it again. You're saying I didn't get that. Good for you. Let's see. I got, how about 1,260,399.639. Okay, so that is going to, let's round that to the nearest case. So this 6 is going to round that 9 up to a 0, which will round that 9 up to a 0, which will basically round this up to 400, right? This 399 up to 400. So 1,260,400 cases. What do you think? Do you think it's reasonable to assume that that trend will continue? I'll leave that to you. You decide whether you think. The thing with exponential growth is usually, except with the cases of money, if you're guaranteed 5% interest, yeah, it's going to continue on this kind of a growth, kind of a trend. But if it's representing something like population or this kind of a spread of cases, you know, usually what's going to happen at some point, it's going to level out because it can't continue on this upward trend forever. If we zoom out, we see, you know, this kind of a thing here. We could actually see that problem we just did, a 61. We'd have to pull this all the way down. That 61 cases that we had, we're still not quite there. Yeah, it's just really can't continue on this kind of a trend forever because of such a steep climb. But you decide whether you think it could continue on that trend at least through May 31st. So what we've done in this activity is we've investigated really the difference between a constant rate of change and a constant percent change. Now, the two examples that we just did both had to do with growth, not decay, and we're going to do some decay examples coming up. But what we saw when we were increasing the cases by 75 is we saw linear growth. When we saw that we were increasing the cases by a fixed percent, in that example 15%, we saw this kind of a shape, which is exponential growth. And we could also have exponential decay, which we'll look at in a coming up example, and linear decay, which we have looked at before. So I'd encourage you to take a few minutes and just read carefully through this page and think about the two examples that we did, and then refer back to this page after we do some examples of decay.